I'd like to introduce our next speaker, one of our sponsors, Cornelis Networks, Dr. Robert Bollig.
Some people are still coming, so we wait a few more seconds. So maybe as a short introduction, because my name is not on the slides itself, I'm actually a quite recent addition to Cornelis Networks. So in my past life, 1 year ago, I was still a postdoc writing astrophysical stellar simulation codes on MPI. And I know what scientists hate the most, and that is porting codes. So nobody wants a vendor-specific hardware. Nobody wants to make one code version for each individual supercomputer they run on. So vendor lock-in is what scientists want to really avoid the most. So that's also the topic of my talk, how, if you use open standards, how that increases portability and allows any code to run on any HPC architecture and any HPC architecture to support any code. So of course the standard disclaimers, anything may change at any moment. These are all our best predictions and estimates for when things are going to happen. So who is Cornelis Networks? So we are the independent high-performance fabric vendor. We are not bound to any particular architecture, CPU, GPU, or fabric, or well, our own fabric, of course. But we also have gateways to other fabrics so we can interconnect. And we are the Omni-Path fabric. So you may know us from our previous major host, which is Intel. But Omni-Path fabric is not vendor-specific anymore, so it will work with anything. And we are a scalable high-performance fabric. We are really focused on HPC, not necessarily on data centers and clouds, but of course we could theoretically work there. But HPC and latency and performance is really our main focus. So who are we? Basically, we are a new name in the game, but we are not really a new company. So all the people, most of the people in our company have been working in the field for 20 years now. So it all started back in 2000 with a few startups, Silverstorm and PathScale, which was bought by QLogic. And QLogic, you may know, was also an InfiniBand vendor. But QLogic and the Cray Areas fabric was bought by Intel in 2012. And then they formed the Omni-Path fabric, which took the best of InfiniBand and Cray Areas technology to implement their own specific version of the new fabric called Intel Omni-Path 100. And this continued until 2019, until Intel decided, okay, we don't want to do fabric anymore. Let's stop the business. And Cornelis Networks took over the fabric business of Intel in 2020, and now we're a new startup developing new software, supporting all existing customers, and going forward with new technology in the immediate future. So why do we do it? We do it because scale up doesn't work anymore. If you want to improve performance, you have to scale out. And you cannot just scale out. If you have just a bunch of servers, 1 million servers in a data center somewhere, and have a slow fabric, then you just have a bunch of servers and you don't really have a supercomputer. So if you ever try to run accidentally an MPI job on the Ethernet links of 1 gigabit per second, you will know how slow that is and how that's absolutely latency and performance sensitive. So the fabric is really the enabler of any supercomputer. A supercomputer without a fast fabric is not a supercomputer. How do we do it? We have a full software and hardware stack. We do all management. We have the subnet manager or fabric manager. We do the diagnostic software. We enable all the support and all the setup of the fabric from our own software, which is also open source, built on open standards, so the code is openly visible anywhere. You can compile it yourself. We develop our own adapters on PCIe and OCP standards. We have standard 1U edge switches. We also have director switches, which are basically a giant switch that is a fat tree in a box that might be more cost-effective in some cases. We have copper cables, we have optical cables, we have active copper cables, and we also have gateways, so you can connect Omni-Path to InfiniBand, to Ethernet, and we of course hope that in the future we can also support other vendors. What this means is that we are a fully integrated solution end-to-end. We are open, we are built on open software, open standards, and we are interoperable with other vendors using our gateways. So what makes us different to InfiniBand? So InfiniBand is an older standard. It was built on standard MTU packages, which you might know also from TCP/IP. But that means that you have to send an entire package that might be 8K, 4K bytes until you can do any reshuffling in the network. With FLITS, we have a much more granular approach. So we have one FLIT is only 64 bytes. That's the elementary atomic data package, and that is connected into multiple link transfer packets that are then sent continuously. But what FLITS allow us is that we can interleave high priority traffic with low priority traffic. So if you have an MPI storage access that's transferring a gigabyte of data and you have one MPI communication that really needs to arrive the next microsecond, then FLITS allows us to just interleave that one package into the data storage traffic, allowing it to arrive straight from switch to switch to switch without any additional delay. And there was also some talk about that, a myth that Omni-Path isn't doing offload, which is not true. We do both onload and offload. So there's some overhead, because if you want to do offload, you have to instruct the adapter, okay, get me this memory address. It has to go through the PCIe bus to memory, get the data, and send it over the network. But this all adds latency. And if you have a small message, latency means slow transfer rates. If you have a small data package, 8 bytes, 64 bytes, it might already be in the cache of the CPU anyway. Then you just push it out. And that leads to an effective increase of transfer bandwidth compared to a pure offload approach. If the message is larger, of course, above 16K, the transfer times itself actually becomes important. And then we also do full RDMA offload. So it's not true that Omni-Path is just onload. We do onload and offload for whatever it makes sense. And we also have accelerated TCP/IP support, so we also support IB verbs. So we can also do accelerated RDMA over TCP/IP if needed. As we said, we are vendor neutral, so we allow best-of-breed solutions. You can combine any CPU with any GPU, with any integrator, and any storage solution. So it doesn't matter if you use an AMD GPU with NVIDIA CPUs coming maybe. If you combine Intel CPUs with an AMD GPU, everything can be made. You can use any integrator, whichever is the most convenient for you, the most cheapest. And we can try to work with every storage vendor, so we have no bundling, no exclusivity agreements, nothing. We'll work with anybody, just come talk to us, and we'll try to find a solution for you. And because we are not InfiniBand, it's really important that if you write a tender for any fabric, it's important that you write not we want InfiniBand, because like you say, oh, we will just Google things. No, Google became a replacement for search. So InfiniBand became a replacement for high-performance fabric. No, it's important that you actually write down, we need a high-performance fabric, then we can get into the play, and then you can choose freely what is the best solution for you. So we are also working on our software, as I said. Previously, we were an Intel house. Intel did proprietary software. Now we are independent, and now we do fully open source software. So what we do is we do not use the old PSM2 fabric interface anymore. We use OPX, which is fully built on open standards, open fabrics, so libfabrics. And there was a talk before that libfabric is not a native path to the hardware. No, in our case, libfabric really is native access directly to the hardware at full performance. It's a perfect semantic match between the OFI libfabric API and what is sent to the hardware. This allows us to access industry standard frameworks, so if any middleware implements an OFI interface, we will automatically work with that middleware. And it's ongoing open source development. If any developer hacks together a wrapper or a shim for OFI to any of their implementation in their library, then it will also work. So any community will immediately enable our hardware to run with that software. And we do not do it just for next generation hardware, we do it also for existing Omni-Path deployments. So if you have an Omni-Path cluster anywhere, somewhere, you can upgrade the software from PSM2 to OPX and enable access to all these upcoming middlewares. And forthcoming, our entire architecture, all the next generation switches and fabrics will be built upon this OPX provider. So where do we stand now or previously? As I said, In the Intel days, we only had PSM2, and PSM2 mostly just supported MPI. So it was kind of limiting. It was running on our 100 gig adapter. It was really highly tuned over many years to give the best performance bandwidth-wise on that adapter hardware. But with Omni-Path Express, we enable us to choose at runtime, okay, you just download the OPX provider stack from GitHub, from the libfabric provider homepage. It will compile, it will run immediately without any dependencies. And you can select at runtime FI provider OPX, and it will work immediately without any overhead. And that gives you access to GPUs if they implement appropriate OFI interface. It allows you access to any PGAS and SHMEM schemes, which are partition global arrays. It allows you to use any of the collective libraries used in AI training, and also access to object storage systems like Deos or any other vendor or any other object storage provider. And for CN5000, which we call our 400 gig adapter hardware, this same provider will work. So you can test tomorrow's software on today's hardware. Exactly. You can test tomorrow's software on today's hardware, and therefore program and develop all your applications to run without any problem, to run also in the next several years, test your hardware, optimize it, get it running at full performance. So how does the software stack look like? As you can see, we have an IB verbs provider that allows TCP/IP over IB. We have storage support using that provider. We have PSM2. It only supports mostly MPI, but you can see already Intel MPI already deprecated any support for PSM2 directly. Intel MPI surprisingly stopped supporting its own provider and completely switched to open fabrics. So it was also, they also had to write the shim for UCX or other providers that were still vendor specific. But with OPX, we have full native performance for Intel MPI, Open MPI, MPitch, MVAPitch, and other novel schemes like GasNet, Chapel, SHMEM, Charm, Deos. We will have GPU support using also open standards if the vendor allows it. And we will have support for AI training frameworks, PyTorch, TensorFlow, RSockets, because then the community is developing for us developers, allowing OFI interfaces to work also for these workflows that are more focused on Ethernet or other commodity technologies used in cloud centers. And the advantage is that the OPX really is the direct pathway between your middleware, your software, to the hardware, over the network to the next adapter. What we've also done, because OPX is a completely new provider, we've really tuned the code to make it as lightweight as possible. As I said, for very small messages, we do an on-load approach. So we do the processing on the CPU as quickly as possible using as least amount of cache and instructions wherever possible. So we optimize our PSM provider down to less than 50% in terms of instruction counts. We use much less cache lines. We use much less cache and accesses, so we don't pollute the cache when we do our transfer. We just take the data from cache over the adapter, over the fabric, into the next computer. And we make sure that every commit is checked for regressions. So we never want to become more heavy in overhead as time goes on. What this allows us is to have significant performance improvements. So here we have a standard OSU ping pong. This is the full latency from one computer to another. This is not hardware latency or any other kind of abstraction. This is what the actual user would see. And we get on current hardware, this is, I believe, Ice Lake. This is AMD EPIC Milan. So we did testing on both Ice Lake and AMD. And on AMD, we get down to one microsecond. And because we are doing onload for these CPUs, if you go to the more advanced CPU, we actually go below 1 microsecond. So for example, on Sapphire Rapids, we're down to 0.8 microseconds for a full MPI send receive. And this onload also allows us to push more messages over the adapter. If you have more cores on the CPU, you immediately increase the amount of messages that you can push out. And that's really important if you have workloads that really send all-to-all messages, because then your communication grows by n squared. So even if you have only 1,024 tasks in your job, it will mean it will have to send 1 million messages to just do one all-to-all if it doesn't use an optimized communication algorithm. And there, compared to PSM2, we have doubled the performance on existing hardware. So we're really pushing the old hardware to the maximum, and that will also carry over into the new hardware, which will also push to the maximum. And if you go to a new CPU, you will get an even better increase. And that also is because as we increase the amount of PPN, we linearly scale in the amount of messages we can push out, because the more CPUs are involved, the more messages can do the processing, we can do the interfacing between the data and the hardware. It will just scale linearly. We also plan to do GPU support via open standards. libfabric for GPUs isn't fully enabled yet, but we are hoping that AMD and Intel will fully implement the DMA buff standard, which is basically just part of the Linux kernel. It's not vendor specific. It will run on anything, and it will allow direct RDMA access from the adapter onto the GPU using this DMA buff, I guess, memory mapping technique. And that will also allow us to implement the respective collective libraries used by each individual vendor, which is NCL, RICL, or 1CLL, and the respective toolkits and GPU direct technologies. For NVIDIA, we will probably have to do a custom solution because they might stay with GPU direct. But the plan really is that we want to support any hardware and any GPU and any CPU where possible. So to summarize, what makes Omni-Path Express so software? It's fully built on OpenFabric's interfaces. It's standardized and portable. And I said that's what scientists really do care about. And I hope that the computer centers also really do care about if they talk about containers and libfabric containers and so on. So we can see that directly the benefit that libfabric has on any technology. It is feature-rich, it's an open standard, it can work with anything as long as there's community support for it. We do not need to wait for a vendor to implement something custom for us, it will work directly out of the box. It simplifies the communication layer because you won't have to implement a provider for UCX, for PSM2, for Slingshot, for Rocky or anything. You just have one single provider that you need a program for and it will work. And that gives us broad software support, and because it's open source, you can look at the code, you can tune it to your use case. If you want to switch around, if you want to, for example, tune the onload offload size, you want to do only purely offload, you can do it by just changing the code, and therefore becoming either purely onload, purely offload, doesn't matter. You can configure it the way you want it. And that makes it future-proof because it's an open standard, it will not deprecate. As long as there's community support for it, it will stay relevant. Even though there might be an XKCD comic that says, oh, there are now 15 competing standards, we hope that libfabric will win out. And OPX, our provider, fully embraces these OFA technologies. They are optimized for modern technologies. They're optimized for 400 gig and 800 gig hardware and for current hardware. It allows us significant performance and capability enhancements because we enhance the code and optimized as much out of it as we can. And it allows a seamless transition to future Omni-Path architectures. So if you have an existing cluster, it will work with future technology, no problem. And one important point that our software director stresses regularly is that we're an upstream first company. So every software update we publish is published to the GitHub repo of libfabric. It is checked by Linus Torvalds himself. It is checked by the Linux community and all developers, and only then does it go out to customers. And we don't have, we also have software packages that we produce ourselves with official support and testing, but that is exactly the same software that you will find on the GitHub repo. You get full performance out of the box using only public source software. The same we do for our kernel drivers. So our kernel drivers are fully open source. They are written inside the Linux kernel. They are in tree and they work out of the box. You do not need to update your drivers. You do not need to worry about, okay, I downloaded this driver and then suddenly this other thing doesn't work anymore and I get crashes and I can't use my other GPU anymore or something. No, everything works out of the box. That's our main mantra. We also support all the dominant Linux vendors. We support Red Hat, we support SLES and derivatives, and we also have in work some support for Ubuntu, so that you can also, not in kernel, but you can download it from the package manager and then it will also work. As I said, our main mantra is no conflicts, no choices to be made. Everything just works out of the box. We try to do the same for our switches. So previously we used proprietary management software that was only running with Intel, or now Cornelis Networks Omni-Path Fabric management software. Now we're switching to a purely open source, open BMC management approach. So this allows us to use standard interfaces developed to run on compute clusters. So basically, you can integrate your switches into the same software that you use to manage your compute clusters at the same time because they just work on the same technology. And it allows you to use standard APIs like OpenSSH, HTTPS, Redfish, and it also allows you to use community development, where the community will develop applications for the Redfish API, and then you can use that directly to manage your switches yourself. So now let's come to the hardware. As I said, we have 100 gig hardware at the moment, but we're working on the next generation 400 gig hardware that will come out next year. And in a similar cadence, as soon as PCI Express 6 is available, we will also push out 800 gig hardware, but now with DPUs. So we will also move into the DPU acceleration space using CXL over PCI Express Gen 6. And in 2028, as soon as PCI Gen 7 is out, we will directly go to the respective bandwidth PCI Gen 7 will support. And we changed our naming scheme from Omni-Path to CN5000, CN6000, and CN7000. So that's our current roadmap. So how does CN5000 look like? At the moment, with Omni-Path 100, we get down to 0.8 microseconds. With CN5000, we aim to go even lower, down to what the bare metal hardware can provide and what is limited only by the MPI software. So if you have tried to do an MPI ping pong on, let's say, a shared memory system, which doesn't even touch the fabric, you cannot really go lower than 0.35 microseconds. And we hope that we can get somewhere close to that regime. So where the MPI overhead is larger than the fabric overhead. We also double our message rate. Previously, we could do with PSN2, we could do 150 messages per adapter unidirectional. With OPX, we could double that to 300 million messages per second. With CN5000, we double that again to 640 million messages per second, and we allow 400 gig bandwidth. In addition to these basic hardware features, we also plan to stay fully copper in the rack, and for some out-of-rack connections as well. We plan to offer active copper cables that allow you to reach the neighboring rack up to a few meters. We also, of course, support active optical cables that allow you to do a long-reach cable, and of course, we try to keep costs down. So we always try to keep the most cost-effective solution. What we'll also implement is advanced topologies. So with Omni-Path, at the moment, you could only redo fat trees and tori and other simpler topologies. With CN5000, we will now also support dragonflies and megaflies up to 300,000 endpoints. And dragonflies and megaflies, because they are tapered networks, they have some oversubscription. That means we need to really improve our congestion avoidance techniques. So we have active telemetry where each switch communicates to each other switch and says, okay, I am congested, please avoid me, or you are sending too many messages, please throttle your messages a bit. So these are all advanced techniques, and we'll fully try to expose these telemetries over the OpenBMC interface to the user. So the compute center can tell, okay, this job consumed, for example, this many megawatts of power, which is really important given that the current energy efficiency in the Euro HPC tenders and so on has become really a dominant point. And we have many people asking us, okay, can we get these data out? Can we make this publicly available to the users? And now it would be possible. We also switched the ASIC process to a more advanced process, so we will go to 7 nanometers. And we will stay with FLITS, because we believe that this is the best technology. CXL is moving to FLITS, PCI Express is moving to FLITS, other vendors are also moving to FLITS, so this is really where we see the future is going. CN6000 will implement accelerated DPU. DK Panda already talked many times about what advantages a DPU can bring to cloud centers and to HPC centers. We will again double the message rate up to 1 billion messages per adapter per second, and we will maintain interoperability. So if you want to upgrade an existing 400 gig hardware system to 800 gig, you can do it. You can have islands of 400 gig, 800 gig, even 100 gig working together inside one cluster, and they will just plug into each other. Of course, if you plug in a 400 gig adapter into an 800 gig switch, you waste an 800 gig port, but theoretically it's possible. So you can have individual islands of mixed technology in one unified network. So how will the DPU look like? We will go, again, open standards. We will use RISC-V CPUs. We'll put quite a few on them. We haven't fully decided how many, but we will also use fabric accelerator units. So if you want to do stream processing on 80 gig per second, you cannot do it over RISC-V, they are too slow. So we use dedicated hardware that can do simple operations on the entire data stream every second. And we do not try to be just an infrastructure processing unit. So we're not trying specifically to enable cloud center deployments. This is mostly focused on HPC. Of course, because they are RISC-V CPUs, you can use them for anything. They are freely programmable. You can run Linux on them. You can do whatever you want with them. But our main focus really is how do we leverage DPUs to accelerate your HPC workloads? So what are some use cases we can see? As I said, we can do programmable offload to the DPU, full offload, no CPU anymore. If you do want to do non-blocking collectives, you can let the DPU handle all of that for you. So that increases the application performance. If you want to do collectives have to do some calculation. They have to do an MPI add, MPI subtract, or whatever. You can also run that on the RISC-V cores. Therefore, doing full in-network compute without needing to cross that PCI Express link congestion link interface. You can use them to run your own compute tasks. You can run scheduled MPI tasks to run on the DPU to do something. Let's say you want to do an FFT on there, you want to do mesh rebalancing. You can offload that on the fly, so you can have it have your mesh rebalanced on the DPU while you continue computing on the CPU. And we will also have memory on the DPU, so you can offload. You can do it in parallel, so you do not need to do RDMA over the memory bus to the memory, do your calculation there. No, you can do it on the adapter itself. And because it's RISC-V, you can do infrastructure offload. You can let it run your storage system. You can let it run your software-defined networks. You can do your drop isolation, your encryption, and so on. All of this can be done on the general RISC-V chips. So what are the advantages that Cornelis Omni-Path brings to the table? These are really the 6 Ps. We have high performance, we have lowest scalable latency, we have highest message rate, and we have high data throughput and bandwidth given the technology. But what we see is that for most applications, the lowest latency and the highest message rate really are most important thing. For normal HPC applications, these are the metrics that matter. Many don't really benefit as of now from 200 gig or 400 gig. Because energy efficiency is also really important, we are leading in energy efficiency. And because of energy prices, that also means we are leading in price. Not only from the power consumption point, but also from the cluster setup point. We have leading product innovation using our FLITS technology up to 400 and 800 gig. That also means we do not have forward error correction, we have lowest latency, we have link level retry, and no matter how congested or what the quality of your links are, we will always have lowest latency and highest scalability. And we are partner friendly, so there's no bundling, no bid conditions. All that matters is that you write your tender correctly so that we can play in the game and reduce your costs. And we have really high product availability. If you want your cluster the next month with Omni-Path 100, we can do it today. So with this, I would like to thank you for your time, and I'm open for questions.